Hello. So first of all, I would like to thank the organizers of this edition of the Nearly Carbon Neutral Geometric Topology Conference for giving me the opportunity to speak here today. So I will be talking about the study of the infima of certain notional volumes for convex or compact hyperbolic free manifolds. And in particular, I will be focusing on the dual volume on the convex core and the renormalized volume. So I'll start by giving a brief overview of the properties of convex or compact manifolds and their deformation space. So let's start first by taking a complete hyperbolic free manifold M. So the quotient of the hyperbolic space by a discrete and torsion-free subgroup of isometries, which I'll always assume to be orientation preserving. So the limit set of the subgroup gamma is then defined as the set of accumulation points in the boundary at infinity of H3 of a given orbit by the action of the group. Then we define the convex hull of the limit set to be the smallest non-empty gamma invariant convex subset inside the hyperbolic space. And we set the convex core of the manifold M to be the image of the convex hull in the quotient by the action of the group gamma. Then we say that the manifold M is convex or compact if the convex core defines a compact subset of the manifold. So given now a compact free manifold with boundary N, we denote by CCN the deformation space of convex or compact structures on the interior of such manifold. So in particular, a set of structures up to the action of the diffeomorphisms isotopic to the identity. So one way to describe this deformation space is by looking at what happens on the boundary at infinity. So to be more precise, first let's recall that the isometry group of the hyperbolic space acts on the boundary at infinity as PSL2C acts on the Riemann sphere. So if we consider now the complementary region of the limit set, we obtain a gamma invariant open subset on which the group acts freely and properly discontinuous. So as we take the quotient by the action of the group, we obtain what is called a complex projective surface. So this type of structures can be encoded by two data. So first we have a conformal structure that we denote by C infinity. And second, we have a holomorphic Araki differential, which roughly measures how far is the complex projective structure from being of Fuchsian type. So from being conjugated into PSL2R instead of PSL2C. So if we just focus on the conformal structure, we can actually describe a parametrization of the deformation space of convex or compact structures. So to be more precise, what we see is that if we select a conformal structure on the boundary of the manifold, then we can find a unique convex or compact structure with that conformal structure at infinity. And the in-use map from Teichmüller space to the deformation space of convex compact structures turns out to be the universal cover of the deformation space itself. When the boundary of the manifold is incompressible, then this map is actually a global homeomorphism. So this is very briefly what concerns the structure of the boundary at infinity of our manifolds. But we can actually say something about the boundary of the convex core as well. So the boundary of the convex core has the structure of a pleated surface. So it is almost everywhere totally geodesic, and the locus where it fails to be smooth is described by a geodesic lamination. So it carries a hyperbolic metric that is obtained by gluing the totally geodesic pieces together. And on the geodesic lamination, we can define what is called the bending measure, which is a measured lamination that tells us how much the surface bends as we move transversely to the geodesic lamination. So once we have a hyperbolic metric and the measured lamination, we can also define a length of the bending measure that in the case of a rational lamination is simply the weighted sum of the lengths of the simple closed curves appearing in the geodesic lamination multiplied by the exterior angles. So if now we look at the boundary of the convex core and the boundary at infinity on a side, we see some similarities. So if on one side we have a hyperbolic structure, on the other we have a conformal structure. If on the convex core we have a bending measure that tells us how much the surface bends, on the other we have a measured foliation, which is obtained as the horizontal foliation of the Schwarzschild infinity. As we define the hyperbolic length of the bending measure on one side, we can also consider the extremal length of the horizontal foliation of the Schwarzschild infinity with respect to the conformal structure. So this is more or less all we will need to know about the structure of convex or compact manifolds. So I will now give a brief introduction of the notion of volumes that we will be interested in the rest of the talk. So I'll start by giving a description of the dual volume for convex or compact manifolds. So let's start by taking a manifold M, and let's consider D a region of M that is convex and with regular boundary. We then set the dual volume of such region to be equal to the Riemannian volume of D minus 1/2 the integral of the mean curvature, where here by mean curvature H we mean the trace of the shape operator on the boundary on the convex domain. So if we try to apply the definition of dual volume for less regular domains, what we can do is going by approximation. And so what we see is that as we take convex domains with regular boundary that get closer and closer to the convex core of the manifold, the integral of the mean curvature on the boundary converges to the length of the bending measure. And so this is how we define the notion of dual volume of the convex core by this approximation process. Okay, so this is all we wanted to say about the notion of dual volume. So let's now move on the renormalized volume. So the renormalized volume was initially introduced in the work of Itten and Graham, and it was motivated by the anti-de Sitter conformal theory correspondence in a more general setting. So it has then been studied more specifically for convex or compact free manifolds in the works of Takhtajan, Zograff, Theo, Krasnov, and Schlenker, who highlighted in particular the relations of this function with the geometry of the effect Euler space. So I will give a presentation of the renormalized volume, which passes through a geometric foliation of convex or compact manifolds, which is a foliation by K-surfaces. So what we mean by a K-surface is an embedded surface inside the free manifold M, such that the intrinsic metric of the surface has constant Gaussian curvature equal to K. A result due to Laborie then tells us that the complementary region of the convex core of the manifold is foliated by K-surfaces. So each leaf has a constant curvature, and as the leaf moves towards the boundary of the convex core, the curvature gets closer to -1, and as the leaf goes towards the boundary at infinity, the curvature goes to 0. So using this foliation, we can now define the renormalized volume of a convex or compact manifold in the following way. So first we introduce a parameter just for convenience, parameter t, and then we set the curvature as a function of t to be given by this expression. So then the quantity that we compute is the following. We take the average between the standard Riemannian volume and the dual volume of the region of M enclosed by the K surfaces. And then we remove a linear function in T, depending only on the topology of the boundary of the manifold. And so what happens is that as we take this limit for T that goes to infinity, we obtain a finite limit. And this process defines a analytic function on the space of convex or compact manifolds with a fixed topology, which is what we call the renormalized volume. So the reason why we introduced the dual volume of the convex core and the renormalized volume together is that they actually display a nice similarity with respect to the picture that we were looking at before when we were studying the geometry of convex or compact manifolds. So to be more precise, if we go back at the table that we were looking at before, comparing the boundary of the convex core and the boundary at infinity, we see that the variation formulae of the dual volume of the convex core and the renormalized volume have the following expressions. So on one side, we have that the variation of the dual volume is up to a multiplicative constant equal to the differential of the length of the bending measure applied to the variation of the metric. While on the other side, for the renormalized volume, we have that the variation is given by the differential of the extremal length of the horizontal foliation applied to the variation of the conformal structure at infinity. And so from this picture, we see a nice connection between the two notions and these ways of describing the structure of convex or compact manifolds in terms of the boundary of the convex core or the boundary at infinity. So this is almost all I wanted to say about the notion of volumes that we will be interested in. So let's now move into more precisely the topic of the talk, so the study of the infima. So the results that I would like to talk about are the first given by Bridgman, Brock, and Bromberg, which concerned the dual volume of the infima of the renormalized volume, and the second by myself concerning the infima of the dual volume of the convex core. So the result by Bridgman, Brock, and Bromberg tells us that when the free manifold has incompressible boundary, then the infimum of the renormalized volume on the deformation space of convex compact structures is equal to the infimum of the volume of the convex core. And so what it turns out is that the same can be actually said for the dual volume of the convex core. And moreover, in both the cases, we have the equality between the renormalized volume and the volume of the convex core, or the dual volume and the volume of the convex core, if and only if the boundary of the convex core is Dott-Legge-Hessel. So we can actually compare these quantities using a chain of inequality due to Bridgman, Brock, and Bromberg. So what it turns out is that the dual volume of the convex core is always less or equal than the renormalized volume, that is also less or equal than the volume of the convex core. So in particular, we know this gives us already a chain of inequalities between the infima. And it also tells us that if we know that the infimum of the volume of the convex core is equal to the infimum of the dual volume of the convex core, then the same has to be true for the renormalized volume. So we can see that the statement for the dual volume of the convex core is a slight improvement of the one concerning the renormalized volume. And so and one last thing that I wanted to underline here is that the hypothesis of incompressible boundary is actually necessary. And the reason is that it is possible to find examples of manifolds with compressible boundary whose renormalized volume is strictly less than zero. And so in particular, for this type of manifolds, the infimum of the renormalized volume will be always negative, and which is not possible to be equal to the infimum of the volume of the convex core, which is always a non-negative quantity. And since we have this chain of inequalities, the same is true for the dual volume of the convex core. So we can now briefly describe the strategy applied by Bridgman, Brock, and Bromberg in the study of the infimum of the renormalized volume. And so we will then try to apply the same type of argument for the dual volume of the convex core. So what we do is first we start by picking a convex or compact manifold, and then we look at the renormalized volume as a function on the Teichmüller space of the boundary. And so here we are making use of the identification between the formation space of convex or compact structures and the Teichmüller space of the boundary. So we can now consider the vector field given by minus the gradient of the renormalized volume. Because of the variation formula of the renormalized volume, and because of the incompressibility of the boundary, we see that this by Peterson gradient has an infinity norm that is uniformly bounded. And this follows by the Nehari bound on the Schwarzschild infinity. This fact guarantees that the flow of minus the gradient of the renormalized volume is defined for every time. And so what we can do now is we can express the renormalized volume at time 0 minus the renormalized volume at time t as this function in the in the gradient of in the norm of the gradient of the renormalized volume. So now, again, because of the incompressibility, we see that the left side of this equality has to be bounded from above. In particular, the right side of the equality has to converge as t goes to plus infinity. So if this integral converges, we then have that there has to be a sequence of times Tn for which the norm of the gradient has to go to 0. In particular, if now we make use of a lower bound of the renormalized volume, it has the following form. So we can say that the renormalized volume of the manifold is larger or equal than the volume of the complex core minus a function that is a continuous function that is equal to 0 at 0. And so if we flow along the, so if we move along this sequence of times, we see that the norm of the gradient is decaying. And so the difference between the normalized volume and the volume of the complex core is going to 0. So this in particular implies that the initial renormalized volume is always larger or equal than the limit for n that goes to infinity of the normalized volume of the manifolds at these times, Tn, and these renormalized volumes are larger or equal than the infimum of the volume of the complex core because of this inequality here. And so this is all we need to deduce that the renormalized volume of our initial manifold is larger or equal than the infimum of the volume of the complex core. So we would like to apply a similar type of strategy to the dual volume of the complex core. And the main problem that we encounter at the very beginning is the fact that if on one side we know that the conformal structures at infinity parameterize the deformation space of convex or compact manifolds, we do not know the same for the hyperbolic matrix on the boundary of the convex core. It was conjectured by Thurston that the hyperbolic matrix on the boundary of the convex core are in bijection with the convex co-complex structures. And so if you are not allowed to consider the dual volume as a function on the Teichmüller space, we have to find another way to attack the problem. And so what comes in hand in this situation is a property satisfied by K-surfaces that has been proved by Labourie and Schlenker. And so the result that I'm thinking about is tells us that the space of convex or compact structures is parameterized by the hyperbolic matrix on the K-surfaces inside our manifold M. So in each end of this manifold, we have a K-surface, and the data of the hyperbolic structures on each of these K-surfaces gives us a way to parameterize the convex or compact structure on the manifold. So what this allows us to do is we can, instead of studying the dual volume of the convex core, we now look at this Vk star volume, that is the dual volume of the region enclosed by the K-surfaces. We can now consider this as a function on the Teichmüller space of the boundary, and in particular look at its Weil-Petersson gradient. Using the properties of the dual volume, we can express this gradient in terms of the geometry of the K-surfaces. And so here is an explicit description of the Weil-Petersson gradient, which involves the geometric invariance of the K-surfaces, so the second fundamental form, the first fundamental form, and a function u that is determined by a PDE involving the mean curvature of the K-surface. And so the first step is to understand whether the flow of this vector field is defined for every time. And so here we need to use again the fact that the boundary of the manifold is incompressible. And so because of this, we see that the n infinity norm of the Weil-Petersson gradient of the Vk star volume is uniformly bounded on the Teichmüller space. And so instead of using the Nehari bound, Here, the properties that come into play are a compactness criterion for K-surfaces and some standard inequalities of elliptic regularity concerning this PDE satisfied by the function u. And so out of these properties, we deduce that the flow of the Wright-Peterson gradient is defined for every time. And so we can express the VK star volume similarly to what was done for the renormalized volume. So we look at the difference, we express it in terms of this integral in the norm of the Wright-Peterson gradient. And we see that, again, because of the incompressibility of the boundary, the left side of this equality has to be bounded from above. So again, the integral on the right has to converge, and so we have a sequence of times for which the norm of the gradient goes to 0. We now need an inequality that relates the integral of the mean curvature with the norm of the Wright-Peterson gradient. So the inequality can be obtained from the explicit description that we gave of the Wright-Peterson gradient, and it is the inequality that we write here. So it tells us that the integral of the mean curvature, that is the term that appears in the dual volume in the definition of the VK star volume. So this quantity is bounded from above by the square norm of the Wright-Peterson gradient of the function VK star, and a term that depends only on the topology of the boundary and the curvature K. So what we can do now is we can say that the VK star volume of the initial point is always larger or equal than the lim sup of the standard Riemannian volume of the region enclosed by the K surfaces for the manifold at time Tn, plus this function that depends only on the topology of the boundary and the curvature K. So this tells us in particular that this quantity here is larger or equal than the infimum of the volume of the convex core plus a function that in particular goes to 0 as K goes to -1. And so the last remark is to observe that as K that goes to -1, so as the K surfaces approach the boundary of the convex core, the VK star volume goes towards the volume of the dual volume of the convex core. And so here, in this chain of inequality, tells us in the end that the dual volume of the convex core is larger or equal than the infimum of the volume of the convex core, which was the statement that we were looking for. And so this concludes the proof of the result concerning the infimum of the dual volume of the convex core. And as a last remark, I wanted to mention the fact that so this statement in the quasi-Fuchsian case tells us that the dual volume of the convex core is always larger or equal than 0. So what we can say is that actually the inequality given by this statement, so the fact that the volume of the convex core is larger or equal than 1/2 the length of the band we measure, is optimal with respect to the multiplicative constant appearing here in the statement. So if we increase this multiplicative constant, then we can always find a quasi-Fuchsian manifold that does not satisfy this. And the place where this inequality fails is always close to the Fuchsian locus. Okay, so this is all I wanted to say for the study of the infima of these notional volumes, and so I thank you for your attention.